So far we've looked at magnetic fields, and we have a couple of equations that include a term that tells us how strong the magnetic field is. That's either related to some force or some of the properties of the current in a wire or something like that. I can also use a sensor to figure out how strong a magnetic field is. Today we're going to talk about something that's related to that called magnetic flux. Magnetic flux is essentially a way of describing how strong a magnetic field is. If this little box that I have drawn here is a magnet, then coming out of the end of that magnet are field lines, right? And those field lines might look something like this. We know that these field lines are parts of closed loops that would circle all the way around from this pole to the other pole of this magnet and then through the magnet. But I'm just drawing part of the field lines. Next, we're going to imagine a little circle that I'm drawing at a certain point away from this magnet. So maybe right here. So here I have like a three-dimensional little loop that I'm placing at that location that's just away from the edge of the pole of the magnet. And if you imagine that little circular loop or that circular plate as being perpendicular to the axis of the pole of that magnet, then there are a bunch of lines that are going through from the pole through the plane of that little loop that I've drawn. And if I were to take that and move it further away, so I take that same loop and I move it out here, then there would be fewer magnetic field lines going through that loop. Now, magnetic field lines are not things that exist, right? They're things that we draw. But the relative distance between magnetic field lines tells me how strong the magnetic field is. And so when I'm closer to the end of the magnet, there are more lines that go through that loop. And when I'm further away from the end of the magnet, the pole of the magnet, there are fewer lines that go through that loop. And a very vague and generic description of what magnetic flux is would be to say that when there's more lines going through the loop, there's more magnetic field or a stronger magnetic field, and so for that reason the flux is higher. There's more field lines going through. And so as we move the loop further away, the magnetic field decreases, and we can describe that as there being fewer field lines going through that loop. And so that's how we're going to develop this idea of magnetic flux. As an equation, we're going to represent magnetic flux in this way. We'll use a Greek letter phi to represent magnetic flux, which looks something like that. It's kind of like a circle with an I over it. And we'll use the subscript b in the same way that for F subscript b that meant magnetic force. Here, phi subscript b will represent magnetic flux. Magnetic flux is equal to, I'll write it out and then we'll describe each term. It's equal to A times B times the cosine of theta. So this is our equation for magnetic flux. The A in this equation represents the surface area that's being used to calculate the flux. So letter A stands for surface area. So inherently, an area should be measured in meters squared, right? So the units of that term will be meters squared. The next letter in this equation is B, and B represents the component of the magnetic field that's perpendicular to the surface A. So the component of B that is perpendicular to A, and B is measured in Tesla, so I'll include the unit there. And lastly, the theta in this equation represents the angle between the direction of the magnetic field and a line that is perpendicular to the surface A. And I'll show a picture of this in just a moment. But theta represents the angle between the magnetic field direction and a line perpendicular to the surface of A. So if I take one of the loops from up above and I wanted to show you what a line perpendicular to the surface of A looks like, then here's that loop. So you can imagine part of that loop is coming out of the screen, part of that loop is going into the screen. And here's a dotted line that's perpendicular to that loop, right? And so a line that starts at the center of that loop and points perpendicular to that loop would look like the following, right? It would start there and come out away from that loop. Okay, so that's a line that's perpendicular to the plane of the loop. And now if, for example, we take that loop and place it in the region of, which is not an actual loop, right? It's just a thing that we're imagining, some loop with a surface area A in order to define what the magnetic flux is. If we place that loop in a region where there's a magnetic field, and maybe the magnetic field is directed to the right like this, then the line that points perpendicular to the surface of that loop still looks like this, right? And so what is the angle between the direction of the magnetic field and the line that's perpendicular to the surface of A? That angle is 0 degrees, right? So in the picture that I've drawn here, theta will be equal to 0 degrees. And the cosine of 0 degrees is equal to 1. And this should make a lot of sense, because if the line coming off of the area that we've drawn, which is perpendicular to that area, and the magnetic field point in the same direction, then we're getting the most amount of flux. And so the cosine term is included in this equation because in instances where the angle is 0, as in the picture that I've drawn, we want the equation to give us the maximum amount of flux. And then if B were at some angle relative to the loop, then we wouldn't get as much flux, and the cosine term would allow us to get the correct amount of flux going through the loop. Okay? And so the magnetic flux is defined in this way with this equation, and the angle is something that's really important and tricky to understand, but hopefully that picture helps. Lastly, if we look at the equation for magnetic flux, B is in units of Tesla, and area is in units of meters squared. The angle is thought of as being unitless, right? And the unit for magnetic flux is the following. 1 meter squared times Tesla, which is the units we have in this unit for magnetic flux, is equal to 1 Weber. And Weber is abbreviated with a capital letter W and then a lowercase letter b. So Weber is going to be the unit that we'll use for magnetic flux. The last thing I'd like to do here in describing this first part of magnetic flux would be to show you an example where the magnetic field wasn't aligned with that perpendicular line as I've drawn. And something might look something like this, right? Here's my loop, and the magnetic field, instead of being to the right, is directed at some angle like this. In this kind of a situation, the line that points perpendicular to the surface of the area A would look like this, and the angle between that line and the magnetic field direction would be this angle here, right? So theta would be defined in that way. And because that angle is not 0, then of course we'll get some fraction of the magnetic field that we had down, or some fraction of the flux that we had down in the lower picture. Right? And of course you can imagine the extreme scenario where the magnetic field was directed up, but the loop was oriented in the same direction. And in that kind of a scenario, the angle between the line and the magnetic field would be 90 degrees, and the cosine of 90 degrees is equal to 0. And so the flux would be 0. Right? If my magnetic field were going up like this, and my loop was oriented this way, although I'm drawing it as though maybe it looks like that line's going through there, three-dimensionally, the magnetic field going up and the plane of that loop being perpendicular to that, it would mean that there's no magnetic field going through that region, and so the flux is defined as being 0, right? Because the angle between this line and the magnetic field direction is 90 degrees, and the cosine of 90 degrees is 0. Now I'm going to take what we just learned about previously and apply it to something that is crucial to our understanding of how electricity and magnetism are related. If I take a magnet, right, the same type of magnet that I had in the previous part of the video, then it's got a magnetic field around it, and maybe it's got some magnetic field lines that look something like what I'm drawing here. And if once again I draw a loop next to that magnet, but instead of it just being some arbitrary loop that I'm imagining, it is a physical conducting wire. If you imagine taking that loop of wire and bringing it next to the magnet, initially it doesn't do anything. But if I start moving the magnet, or if I start moving the loop of wire back and forth, so maybe for simplicity the wire is held in place, and I take the magnet and I'm moving it to the left and I move it to the right. It's being moved back and forth through this loop. If you look at the magnetic field lines, as the magnet moves back and forth, the flux through that loop is changing. And this change in the flux through that loop gives rise to an induced EMF. We induce an electromotive force, or like a voltage, in the loop of wire, which causes a current. And so, what am I saying? The rate of change in that flux would be given by the following. Delta phi b, which is the quantity flux that we talked about on the first part of the video, delta phi b divided by delta t. Just like anything that's divided by delta t, this is a rate of change in the flux, delta phi over delta t, gives rise to an electromotive force, which we'll abbreviate with the Greek letter epsilon. The magnitude of that electromotive force is given by the magnitude of this quantity that I've drawn on the right. As the flux changes, an electromotive force is produced in that loop. This is an example of magnetism producing electricity. And we can also see examples of electricity producing magnetism. Right? I'm using a magnetic field and the idea of flux and changing the flux in this conducting loop of wire to produce an EMF, and once I have an EMF in the wire, that electromotive force is going to produce the movement of charges in that loop, and the movement of charges in that loop is a current. So I'm using the magnetic field of the magnet to produce a current in the wire. The direction of that current is given by a law which we'll be talking about shortly. But for now, as long as we understand this idea of flux and how a changing flux can be used to produce a current by induction, then we're in a pretty good spot.